recording. Okay, so welcome everybody to the Silicon Valley JavaFX user group. I'm Steven. This is Keith. We're your CodeJug leaders. Well, big welcome to Michael, who came all the way from Germany just to present to you guys. So thank you. Round of applause. Okay, and some announcements before we kick off. So this is one of the things which we've been working on. So we have a bunch of demos which we've been creating for Java 1 and Oracle Code San Francisco. This one is like if you saw the first Matrix movie where they do the 360-degree shot in slow motion with Keanu Reeves where he dodges bullets. We recreated it using Raspberry Pis and custom 3D printed enclosures and beam sensors to link up the different Raspberry Pis. And we use a lighting track with power converters from 48 to 5 volts to have clean power to the devices. So this is one of the things which we're going to hopefully have working next week. The new one. Yeah, it gives better quality. That's what the actual rig looks like. We set it up and did some filming last week. So we got slow motion film, but not from the cameras. The plan was to actually get slow motion film off the cameras themselves, but we realized last minute that the exactly identical power supply comes in 48 to 12 volt and 48 to 5 volt, and the only difference, the components all look identical, and the only difference is the sticker. And the sticker was down on the devices, so we had to unscrew them to figure out which ones were wrong. So that's fixed, and there's other issues. The other demo, and this one I know works because I was doing this. Maybe it's this one. I was doing the final setup for this at my house last night. So we are working with Alpha Acid, which is a local brewery, and so we instrumented their fermentation tanks and their wort tanks for brewing with a bunch of sensors to get like temperature, specific gravity, pressure, flow control for like how much liquid's flowing. And we're feeding this into our IoT production monitoring and IoT asset monitoring cloud services. And besides the brewery instrumentation, we also instrumented some kegerators, which we're going to have at the conference. So we're going to be serving beer, which was made using this process, at the conference. And we're going to have kegerators where you can vote, and then it keeps track of how much you're drinking. Well, it's anonymous. Your boss won't find out. But you know when the kegs are running empty because we're keeping track of utilization. So it's 4 kegs, 4 different styles. 2 of them are Kyle's regular beers, so Dark Side and Belmonter, which is a porter and a sour, kettle sour. And then he made 2 beers just for the conference. So an Open World IPA and a that's Kyle, the proprietor of Alpha Acids. He's a cool guy. Alpha Acids right across the freeway. They're in that little industrial complex. And on the weekend, Thursdays, Fridays, and Sundays, I think. No, Fridays, Saturdays, Sundays, you can go there and drink beer straight off the tap in the evening at the brewery. The last beer was the Hacker. What was it? Hacker's Den. So the Hacker's Den is a Saison beer. We figured like Saison is the French workers' beer, or Belgium workers' beer. So when the workers would get off the field, they want kind of a light beer to finish the day after hard work in the field. So we figured it matches for coders because you need a beer which isn't too strong so you can actually write code straight while you're drinking. So that's our Hacker's Den beer. This is some of the instrumentation, the sensors you're using at the site that we installed. That's the temperature sensor. And that's Steve Neely. He was at my house yesterday. We were rigging up the kegerators. He works for Relayer. So anyway, drop by the conference if you get a chance next week. We have all these demos running Monday through Wednesday. And how do you get into the conference for free, Bruno?
Yeah, there are 2 ways. You can get a discovery pass, getting $75, which you can spend better with that beer. Um, there's a promotional code on social media, so search for OpenWorld hashtag OOW17 and discover Paladin.
Yeah, so we mailed it out to the user group, but there's a better way to get into the
There's a
conference for
better way,
free.
which you can even get content. So if you register for Oracle Code, which is our one-day conference on Tuesday, with a hand-picked selection of sessions from Java 1, you can attend those sessions for free on Tuesday. But the good thing is that that badge for Tuesday is also good for Monday and Wednesday for the exhibition hall. So you can walk around on Monday and Wednesday and Thursday.
Yeah, but I mean, you get basically like a free conference for a day. So you get the best sessions
Plus
on
30,
Tuesday, picked by Bruno, and Bruno and I went through and picked all the good content. Oh, you just go to developer.oracle.com, and then you sign up for Oracle Code San Francisco, which is right here, San Francisco.
or /code, just go to /code.
Well, I mean, if you click on events, it takes you there,
Yeah.
and you sign up for the San Francisco event. Yeah.
You can attend 33 sessions. Can you go to the agenda so people can have an idea of what sort of content we have? We also have hands-on labs. So you can attend, we have a hands-on lab from Docker Inc. about Docker 101. And we have other two hands-on labs, one about chatbot, building chatbots, and the other one about something that I forgot. Because it's over 100 content, so it's like cannot remember everything. But there's a lot of content around Java development, JavaScript, Python, databases, containers, microservices, REST, API management, DevOps culture. I mean, all the cool things that software developers are looking into these days.
Yeah, and then we get tired of sessions, you can have a beer
Yeah.
at our developer lounge.
Oh, and there's a concert at the end of the day at Moscone, which you can also attend for free. So, a lot of cool stuff.
Okay, so that was a shameless plug for like stuff that we've been busy working on for the past couple months. But we should perhaps let Michael present. So here's
the HDMI, cool.
HDMI cable back.
Yeah, so thanks a lot for the invitation. I'm glad to be here. And I'm also at Java 1 next week, so we can also chat there. What?
You're here all week.
Yep. Okay, so
If you want to move it, just tell me top right, bottom right corner, or get rid of you.
I think that's fine to have it there. Yeah. So the topic of today is visual programming and interactive visualizations on the Java platform. So my research, so maybe first of all I should tell a little bit about myself. So I'm a computer scientist. I work at the Goethe Center for Scientific Computing at the University of Frankfurt. And I do research in visual programming environments for like simulating highly complex physical processes, and we use a visual modeling language for that, and that's how I got started on this project. But yeah, I evolved from there, and it's now like a completely visual programming IDE. The agenda for today is first we are going to discuss a couple of historical considerations about how applications were developed like a couple of decades ago. And then I would like to discuss two different approaches to visual programming. One is runtime based, and the other one is compile time based. So where you would grab the information, like the matter information about the program, either at runtime or compile time, and it has different implications. And if we have time, we can also discuss a couple of cool applications, like an environment where you can design 3D parts that we also use for 3D printing. So actually there on the table you see some of those parts which have been developed in the environment. So this was one of my use cases. And also you can ask questions whenever you want, or we can discuss a couple of things faster or go more into details if you want. So just tell me. So historical motivations or considerations. When you start a new project, an IDE, you should really carefully think about how applications are developed and whether decisions that have been made are just for historical reasons or if they have other reasons behind them. So when you construct compilers and so on. So when we look back, editing a program was actually a completely non-interactive task. So you would usually have a punch card and write your programs like that. So you would actually not even edit the program on the machine it was compiled at, or would then run later on. And so editing was a completely separate task. There was no relation to the compiler itself. And when you had luck, your code on the punch card would compile into a binary object. And even there, I mean, the editor, even if you had one, would not fit into the same memory with the compiler and the program in the end. So this is why compiling was a separate step, and also finally running the program, and of course debugging and so on. So you had like 3 different phases that you had to go through, and this is still reflected in nowadays tool chains. So we are concerned about editors, compilers, and then the runtime. And but if you look at like the compiler construction manuals, you will find that the compiler still only is concerned about compiling programs and not like interacting with the developer itself. And of course, nowadays we do that in IDE, so we reuse the information. But what people have done, and what to some extent is still done today, is like the compiler and all the useful information about control and data flow is just thrown away after actually compiling the program. So the whole control flow, data flow is reflected in the final binary, but it's not like used at edit time, for example. There are a couple of exceptions, like you get auto completion and maybe some hints in the IDE tells you that you shouldn't do certain things, or it just says, yeah, doesn't compile at all, and it gives you some hints during the development. But it's not like the whole knowledge from the compiler is reflected in the editor. And this is partly due to the reason that the tool chain is split up into different tools, and only gradually we are like merging them together again. So so now let's talk about visual programming. I mean, there have been several approaches to visual programming so far. We just briefly touch a couple of existing languages. So this is the one that I like most. It's, I think, one of the oldest. It's from like the late 60s or so. And somebody wrote his PhD about a visual programming language where you could design your own input symbols and give it some meaning, and then have like a data flow based programming environment, and it would also return the actual data at runtime, and you could like play with the environment there. So this was done on a vector screen. I think it was 1968 or something. This is just the image I got from a YouTube stream where somebody grabbed an old videotape about that environment. So one of the most well-known one is LabView. LabView is an environment also data flow based and rather domain-specific. As you can see, it looks like schematics and circuits. So that's kind of where it's used. So you can do signal processing and it's very powerful, but it's only it's not really a general purpose environment and doesn't reflect an existing programming language. It's builds its own visual language. Then there are a couple of environments like Scratch, Blocky, and so forth that basically do structured editing. So you can just plug the parts of the program together, the structures. But it still basically looks like the textual representation of the program, except that for the structural design, you cannot make typical syntax errors because the blocks only fit together if they are syntactically compatible. So that's nice when you introduce to programming, but it's still not a real programming environment that reflects a programming language that already exists. And I mean, in my opinion, this doesn't scale as nicely as textual programming does. So now, runtime-based versus compile-time-based visual programming. So in my research, I always try to use existing languages, and I use Java and Groovy for that purpose, and extract as much information as possible, and then synchronize that with a visualization. And so what we want to do is to automatically go from the code to the visual representation and back, because it doesn't make sense to have a visual programming environment that just generates code. It actually should talk to each other. Otherwise, it's not as useful. So what you can do is you can do a reflection-based approach. That was the first approach that I did because it's easier to implement. You don't have to re-implement a compiler. And it gives you a lot of possibilities. So I will show you one environment. It's called VRL Studio, where you can basically reflectively interact with all Java objects. So it's completely compatible with Java bytecode. The other approach would be to reuse the actual knowledge inside the compiler, and instead of just throwing that away, you can also synchronize with a user interface. And the nice thing about this is that it doesn't only give you the possibility to reflectively interact with APIs, it also gives you the possibility to really change the code visually. But first, the runtime approach. Do you have any questions so far or comments before we go like deeper into that? Hello. Yeah. Yeah. Yeah, so we'll get into that. Basically, the hierarchical structure, like scopes and data and control flow. So I will show you a program later on and it will become clear. But basically, just like reflection gives you a way to get information about APIs. The compiler-based approach adds like data flow and control flow to that. And it's I'm not so much interested in like what the compiler does optimize and how the performance tuning would go, but we will look into some profiling aspects. But for me, the most important thing is to get everything that's necessary for editing a program. So getting that out of the compiler, like the AST. But we will get to that after the runtime block. For this, I developed the visual programming environment VRL Studio, and the library for that is VRL. It's short for Visual Reflection Library. So basically, it's a framework for automatic GUI generation. you can just specify ordinary Java code, compile it, and then do the visual reflection, which just gives you a small box with inputs and outputs, and of course every method of the object. And you can do some kind of workflow management and visual programming in that environment as well. So the GUI generation works like this. You have the Java object, and then the information, the reflectively accessible information, goes into a so-called object inspector, and it has three main components, like an object representation, which is just a window container, then a method representation, it's a container inside that object representation, and then so-called type representations. And these are really the most custom visualizations that can be anything from a text field to a 3D visualization, anything, or an image. And you, as a library implementer or as a user who wants to extend that, you implement a visual dictionary, like a mapping between data types and visualizations. So that's the only part where you actually have to do UI programming. And the other things are like composed automatically. Yeah, so VRL Studio is available for download. It's free and open source. Here are some of the features. So you can do visual reflection. So you specify source code. It will give you a user interface. You can define data and control flows. And you also have an integrated editor, so you can type Groovy snippets into that. And yeah, we also have a plugin system, built-in versioning, and you can also export projects as regular jar files. So yeah, let's get into that. Oh, it's not coming. Okay, so this is the main environment. You just get this large canvas, and okay, so I notice updating to High Sierra was a bad idea because I lost my menu bar, I think. That's pretty bad. Yeah, I lost the menu bar. This is very bad. So can I just switch machines easily? Can you give me that back? Yeah. Yep, just give me 1 second. I wanted to show you one slide before we go into the demo. So here you see equivalent code. So unfortunately not in JavaFX. Yeah, this is Swing, yeah. But there are still good reasons to use Swing. So I don't like the idea of like replacing one with the other. At least in my workflow, it doesn't work that way. So I have to use both. And so this is what VRL does. You just give it those 5 lines of code. And even as a beginner, you can guess what it actually does. So it adds 2 numbers and returns the result. And VRL will just give you a user interface for doing that, with all like checking that the input actually matches the data type. It will do the execution and do also a visualization of the result. If it's not like just simple text, it could be images or anything else. And something like that would be the code that you had to write. And it's a very compact form. And of course, you can argue that you would be able to see what the code actually does if you do separation of concerns. You can use design patterns to work against that, like model view control. But still, you have to do a lot of work to keep the actual functionality separate from the UI toolkit. And what VRL does, it doesn't do any coupling between the UI toolkit and the actual functionality, and you can still customize the visualizations. So it's these 5 lines against the whole block of Swing implementation, and the Swing code doesn't do really checking validity of the data, and it doesn't do error messages and so on. So you would just end up with runtime exceptions. So that's just a small motivation. And now back to VRL Studio. And I didn't update the Windows machine, then that's why it still works. And as you might have noticed, this is also Swing, even though it has some effects in it. So the first example would be Hello World, of course. It's basically a class with some annotations, but we only look at this hello method right now. And I can instantly compile it and create instances of that code, like so. And I can directly invoke it. And I designed it that way because I really like the idea that newcomers don't have to worry about Ant, Maven, Gradle, whatever. They can just directly interact with code. And if you have small pieces of code, you can... It's almost like a visual shell complement. And you can also change the code. To, let's say, hello California. Then this instance here is replaced. You can invoke it and you get the new functionality. This also works. Let's say we do the integer example again. We create a couple of instances. And now you can do data flow programming. So you can just grab the output of the first component and plug it into the second one. And we could do like 2 plus 3, and we add 1. And if we just invoke the second one, it will figure out the data dependencies. And whenever you invoke something, it's done in a isolated thread, so you can run multiple tasks inside this environment. Um, and what's also very cool is that the environment explains itself. So I can just close those windows. And when you would like to know what this component actually does, you just click on this icon and you get the source code of that. And usually when we work with applications, like you have your web browser and you would like to know what's actually this part doing, where do I get the source code, you are referred to a repository and you have to find out yourself. But in this environment, you can just specifically ask a component, what is your source code, and you can edit it and it will just be replaced if you change the source code. And of course, you can do even more exciting things like creating 3D objects. So in this case, we define 4 nodes in space. We add some triangles and we just return it as a geometry object. And VRL will figure out the data type and replace the text field with the appropriate representation for a 3D object. So it just takes some time to initialize the UI. And this is like the user interface that we get for this. So it's really very interactive. What you can also do is you can go to the shell, and I designed the shell before JShell existed. So this is a Groovy shell, but it's kind of the same idea. You can just add objects, for example. Like I could tell the canvas to add a string. Let's just add a generic string, and we say hello. And now we get oh, I used a capital B. So here we go. This is the string object. And now let's see what we can do with it. So this is also done via reflection. So we're not parsing any source code. We just do reflection on the particular object. So let's just do uppercase, and we get the uppercase hello. So you can just use all the Java APIs and design your own user interfaces. And you can also compose them. So let's say we only want this hello California. So we can take that out of the component. We want this user interface, and we want just to hide everything else. So we can group that, and we can design specific simplified user interfaces, and that's what we do when we work with people like experts from biology or other like life sciences. They get stripped down environments and they can work with that, and they still can change code if they have to. If we tell them, then they can return to the complex version of the UI. Yeah, that's basically the idea. What do you say? Do you like that kind of environment? Do you have any comments about that?
What about custom data types?
Yeah, so you can yeah, okay, that's a good point. So custom data types. You can actually write your own type representations, and you just have to implement 2 methods like set view value and get view value. That's like the transfer that you have to do, and everything else is done automatically. So like type checking, it will also reflect on the inheritance, and so do all the checking for you. And you can customize serialization if you have to. Sometimes data is so large that you wouldn't like to serialize it, or like you want to switch from XML to binary serialization for some data types, and that's what you can do. And you can also implement plugins. So here is a list of plugins that I have installed, and they can provide custom visualizations. And yeah, so that's a really convenient way to reduce the complexity in UI development, because you only have to implement the specific data visualizations, and you don't have to implement the whole application lifecycle. So if you make mistakes, it's probably just in the type representations. yeah, so then I switch back to the other presentation. Yeah, you have one more comment?
Yeah, one more question.
Yeah.
I noticed a lot of the classes that we saw were serializable, and
Yeah.
is there like a way of like saving the state of the whole class?
Yeah. So actually, that's if the classes are serializable and you hit Control S, the whole state is saved into the session file. And the session format is like a zip archive. It has a hidden Git repository in the zip file because most of the users don't know about version control. And then you also save all the states. Yeah, if you don't have, that's a good question. Let's say this sample class isn't serializable, and we remove that. So if I save this project now, you see this object is gone. It was just removed, and there is a warning that some objects couldn't be saved. And the cool thing about the versions is that you get an automatic history, and it also tries to give you like messages that make sense, because usually people say something like minor changes, and commit stuff like that. But the environment will figure out like if you saved a project, if you only changed like the visual state, or if you added a class, if you changed a class or something like that. I will record it here, and it's just a Git repository, so you could even export that. Oh yeah, and I forgot to tell you about the control flow. So sometimes data flow programming doesn't make that much sense. Let's say you call like system nanotime or something, then there is no way to do data flow based programming because there is no input, and then the environment will think it only has to execute this method once, and of course this is not true in this case. So what you could do, you could just align those objects like this, and oops, and you can just connect a control flow like that. And this control flow can also be used to generate source code again. And yeah, one thing I forgot to mention is that this, for example, this code editor is just also created by reflection. So you see it also has control flow inputs and control flow outputs, and it also has an input for the source code here. So this is just a very small object that has a string input and then calls the Groovy compiler inside. So you can do meta programming if you want. So you could write a program that changes actual source code, like you have parameters or something in it, and then you can compile it and add it to the environment, and even the compile toolchain will then be a visual program. Okay. So that's the wrong presentation. So now let's talk about the compile time approach. Now we are using the AST to get informations for creating and synchronizing with user interfaces. And for that, it's very important to introduce language models. So you have to have a model of the programming language that you're trying to visualize. And for my research, I used a subset of Groovy and Java, so just something that you can handle easily, and you could switch compilers without redesigning the language. So the language model basically sits between the compiler infrastructure and the user interface, and it's just an API that allows you to declare compilation units, classes, method, and so forth. So you could actually just use programs as data structures and then manipulating programs by other programs. And this data structure can be constructed either by using the API or by just specifying source code that will be compiled. And for visualizing this, I created a JavaFX based flow library. It's called vWorkflows. It allows you to create large hierarchical graph visualizations. It's available on GitHub. And here are just a couple of samples. So you can style it with CSS. Okay, actually this video doesn't play. Then we just show a live demo later. So this is a visualization of a language model. So you see the source code on the left-hand side and the actual user interface on the right-hand side. And it looks like Visual Studio, but all the connections are done automatically. So you don't have to instantiate objects and then manually define the data flows and control flows. It's just referred from the source code itself. And the design pattern for this looks like that. So you have the language model in the center. This is like the central part of the whole architecture. And the language model can also can be translated into source code. The source code can be compiled to either a jar file or again be compiled into a language model. And now comes the interesting part. The language model can be instrumented. And what I do here is I add all the commands that I need to synchronize with the user interface. So when you run the code, you actually are generating JavaFX events. And the user interface, again, has a direct binding to the language model. So when you close a window or change connections, the language model is modified, and you will also see those changes in the source code. So I just run this now. So, and here you just saw the program compiling the code and then generating the user interface. And that's what it looks like. So, and this is something I use for 3D printing. This is a library called JCSG. It's short for Constructive Solid Geometries. And it was a very nice use case to motivate that kind of development environments. Yeah, you can see that. So what it does, so let's say you have a cube and you have a sphere and you want to compute the intersection, then it will be that part, or you can compute the negative. So you cut out this part of the sphere, or you could express like the union object of the sphere and the cube, which would look like that. And a couple of other operations, and that's a very nice API to programmatically generate 3D objects, and that's the API that we use here. And the interesting thing now is I also want to get to the point where I can just visualize the runtime data, and I want to synchronize. So what we see here is we have basically 3 methods and then one main method, and the one method does, like, it creates a sphere, it creates a cube, and it creates the difference of both. And then we are calling create diff 2 times. So what I can do now in this environment, I can select the source code, and you will see it also selects the visualization here. And when I run the program, and that's now where the instrumentation is used, it gives you all the intermediate results. And that's the important thing. As a developer, you don't have to do anything UI related. I mean, you just write your ordinary source code, but you get basically a debugger on steroids. And you can also interact with those objects. So they are really this is runtime data. So this is JavaX 3D at the moment. And you can also like dive in and just show the subcomponent here and use that as your main entrance point into the program. And a very cool thing is that you can also change the values. So we have now two invocations of the createDiff method, and I don't know if you can, maybe I can zoom in a little. So we have createDiff with those two parameters, and let's now change those in the UI. So we have 1.1 and 0.65, and let's change the 0.65 to something like 0.7. Did you see the change in the source code? And I was changing it in the UI. And the cool thing here is also I cannot introduce syntax errors because the UI checks that the data type matches, but it has a direct binding to the source code. And when you run the program, you see it has like a slightly bigger sphere inside than this one. So you can visually debug your source code. And no debugger will tell you about those differences because the debugger doesn't know anything about your data types. What we can also do is we can add another invocation of the method. I say, okay, let's do createDiff again with let's say 7.1. We compile it again. Did I? So now we have three invocations. That's what you see here. Is there a problem or no? It's just okay. So now we have 3 invocations of the createDiff method. I can also introduce classes like I've done here. I've introduced another class, and the class also has like a container visualization. It has the method container, and it has a reference to this.
So Michael, you have 15 minutes.
Okay. Yep. So what time is it? Yeah. So I showed you both ways. So I can change the source code, it changes the visualization. I can change the visualization, it changes the source code. And it also works with like deleting stuff. So in this class B, for example, I can just close this method window and the source code will be synchronized. And of course, you can add stuff again. So now we have a new window inside the class B. So that's the basic idea. And the whole idea about the instrumentation is that when you run the source code, it generates the JavaX events. And you can synchronize with the user interface, and the user interface generates all the changes to the language model, and the compiler just translates between source code and creates the instrumented version. And the reason why I do the instrumentation inside the language model, so I actually create source code that has instrumentation commands in it, is that I'm much more flexible than the instrumentation infrastructure from the JVM. So I can implement that on other languages as well, and I can also selectively do that depending on which UI framework I use. And now about the profiling. This is just a very basic implementation of it. I just do visualization of the most time-consuming operations, and of course we see it. It's like here the one that actually creates the difference between the sphere and the cube. And for newcomers, it's very intuitive to see the hotspots of the application. This is not accurate, not good for micro benchmarking and profiling, but it gives you kind of a sense of where your actual work is done inside the source code. And it also is a good thing for code coverage. So you see that class B is never used, so there is no color inside the windows here. They stay transparent, and so you have like a feeling for which parts of the program get actually executed and which parts don't. And the cool thing is you only have one design language to teach. In a usual IDE, you have so many different aspects of the user interface that you have to learn. You have complex tree visualizations, you have the source code, like small bubbles in the IDE editor, and a lot of other perspectives that you have to actually learn to get to use that IDE, and I try to reduce that. And of course, this is a research, so this won't replace your NetBeans, IntelliJ, or Eclipse, but it could potentially do that in the future, or you can integrate that with like established IDEs. That's something I would like to do in the future. Okay, so do you have questions or comments about that? About the compile time-based approach? Did you like it, or do you think it's not usable? What's your take on this one? The which domains can you apply that? Yeah, it works when your data is actually visual, like 3D modeling. You could easily use image filtering APIs, and you get direct feedback. So you will easily notice when you like forget the red channel in the algorithm that changes like a filter that changes your image. And also, I think it's usable if you want to create a user interface for people who don't usually program, but they have to communicate with a developer that doesn't do visual interfaces. So you could have somebody uses VI, for example, and hacking on the command line, and you have a user who just wants to play with commands, and the user can use the visualization, and they can work both together. And also here, everything is just saved in the source code. So every change you make is just text in a source code file, so you can easily commit that to GitHub or something, to a repository. Yeah, so that was like the overall like introduction that I wanted to give you today. Yeah, it's yep. So here you have some resources. You can go to viralstudio.mihosoft.eu, or you can find me on Twitter under the Mihosoft, or you just go to my GitHub account and you'll find all the source code and some introduction on how to compile that projects. And so I don't know your name, but you in the beginning you asked about which parts are covered by the language model and synced with the user interface. So if you look into that code, you will also find some experiments about domain-specific optimization that you can do. So this is not only a thing that's visually reflected, but something you can also apply to optimize your source code when you compile the language model back to code. Yeah. So thanks a lot.